So yeah, last time we started to studying the Cooper pair box coupled to a voltage source, and we try to do circuit quantization. So we will continue today. Every step is very important. So last time we showed this circuit, right? So again, whenever you see a circuit, do not rush to solve it. Try to understand what it is. Here we have a Josephson junction in parallel with a capacitor, right? And this forms the so-called Cooper pair box because you can have an extra Cooper pair here, right? And this resembles the LC tank. We have studied LC tank before, that we have a linear inductor, right? A geometric inductor in parallel with the capacitor, and you have a certain resonance frequency. And that resonance frequency will determine what type of photon you can store here. And from there, we showed that it will behave just like a mechanical simple harmonic oscillator, right? For a linear inductor, that you have equal spacing, and one of the possible bases is the number basis, or we should call it fault state, that you can have 0, 1, 2, 3, 4, 5 of number of photon, right? I'm going to erase it, but now just to remind you what I'm talking about, right? This is 0, 1, 2, 3, right? Through quantization, we say the energy equals to h bar omega naught n capital N plus 1/2. Make sense? That was the linear system, right? Now here, we replace this by a Josephson junction. And what is a Josephson junction? We learned all those physics already, so I won't repeat. But last time someone asked, what exactly is this? So we draw this as a cross with a square across it, which means that this is an element that you need to model as the bare Josephson junction. This is the bare Josephson junction, right? And in parallel with a capacitor. And that's what it means, that's it, right? The reason is because Josephson junction is a capacitor by itself, right? Superconductor, insulator, superconductor. Yeah.
What's tau again?
Where? What's that? Tau is just a dummy variable. Yeah.
It goes from negative infinity
to t. So that you will get, actually this is phi of t. Okay, as a function of time. Yeah, but I'm not talking about this, right? I'm talking about this figure, right? So, so is that okay? You understand the situation now? And then we couple this to an external voltage source. And our goal, last time we already quantized this circuit already, right? Without coupling to external source. This time we want to quantize the whole circuit with the external source. Last time we kind of like using some guess method, we did not really verify it. This time we want to go through a more rigorous process of circuit quantization. And I would like you to go through this, and in your assignment you need to do this for another more complicated circuit. Okay? So that is the background, right? So how do we quantize a circuit? First of all, we need to identify the generalized coordinates, momentum, and velocity. Because the process is that we need to find the Lagrangian and Hamiltonian of this system. The generalized coordinates, as we discussed earlier, when we only have this isolated circuit, is the flux, right? And the generalized momentum is the charge. And the velocity is the rate of change of flux, right? In a circuit, usually it is just the voltage, right? And just recall that voltage equal d plus dt, right? And flux, like what you just asked, is just integrates voltage from negative infinity to the current time. So this is already done. And basically, it is the same for every superconducting circuit. Of course, here I did not talk about individual elements, right? Because remember, our system can have many degrees of freedom. So you have the corresponding coordinates for each element. Just like when you have a system of many particles, each particle has its own x, right? So you have x1, x2, x3, x4, x5. Okay? With this, then, we need to figure out the equation of motion of this system. Why do we want to do that? This is because we want to check if our Lagrangian is correct. The Lagrangian we are going to guess later, right? So how do we find the equation of motion? Basically, it just means that you need to find out the governing equation of this system, right? So before that, we define a flux because if we learn from our electrical engineering circuit, we never need to talk about flux when there's no inductor, right? What do you mean by a flux in the branch that you have a capacitor? And how about Josephson junction, right? So we define it as the integration of the voltage of that branch from negative infinity to t. It's just a definition. And because of this, then you will fulfill that the voltage equals to the rates of change of the coordinate, right? So this is this helps us to get the coordinates into the equation. So now every branch has a generalized coordinate. Yeah. Branch, yeah, this one I did not really define it well. Also difficult to define, but basically the branch here is more talking about the voltage across a certain place, right? For my this lousy definition, it's not really like the branch of the circuit. Yeah, yeah. So if you go to the formalism, there will be a better definition. But in that case, you just need to do the right substitution. Yeah. But for now, you just treat it as every voltage you want to treat. But you will find that, oh, this voltage you get, they are not independent eventually. So this is pretty lousy when I say branch. Yeah. But maybe just take it as flux equal to integration of the voltage. Okay. You always ask me difficult questions. So now let's go ahead to do the equation of motion, right? So it's KVL, right? Because in circuit it's KVL, Kirchhoff voltage law, right? So what we're doing, first you need to label the direction correctly, right? We have VA, VB, VC. I label it as negative plus, negative plus, negative plus. So as a result, VA plus VB plus VC equals 0. Right? So anyone who has taken elementary circuit know how to write down this equation. But the good thing is now we already defined this flux, so I can write them as in terms of the general coordinate. So we don't want to talk about voltage, right? This is classical thing, right? So we put this into here. So D plus A, D plus B, D plus C equals 0. Then you just rearrange them. And you trust me, there's no mistake here. Particularly here, I also, VG is the voltage you really apply to it. I have negative sign for it. So I just change psi C dot to negative V dot. Okay, so negative times negative become positive. And then I do one more derivation, right? This is the take another d dt, right? So I get to the second derivative, right? So second derivative of phi b equals the second derivative of Vg minus second derivative of Va. Right? This is just all math. The important thing is that you understand what we are trying to do now. We use KVL, and I write everything in terms of coordinate and velocity. Generalized coordinate. Okay, any questions? Now, naturally, if you try to solve a circuit, the next step, of course, is to find other KVL if you still have some loop that you have not written the equation. But there we don't have, right? But we still have the KCL, Kirchhoff current law, right? The goal, right? The goal. Why I want to do that? Because actually in this system, I can eliminate phi b. I don't care about phi b, this capacitor. I care about this part, right? So the goal is to eliminate phi b. or phi b dot, right? So what is the KCL? I only have two. One is IB. I only have one equation, two currents, IB equal to IA. This one you agree? Yeah? Continuous. So what is IB in this case, right? So I know to save space, I'm going to do this. IB equals to, I will just say QB dot, right? The rate of change of the current is the amount of the charge across this capacitor. The rate of, sorry, say the wrong thing. The current is the rate of change of the charge across this capacitor, right? And if you forgot, just remind you what's the meaning of current. Number of charge passed across section per unit time. That is the meaning of current, right? The definition of current. So IB is QB dot because anything passed through this point will all accumulate at CG. Make sense? So dQB dt is the current. Any questions? Yeah, that's my writing. Dot is here. The red dot is here. Right, let me just write as dQB dt. Okay. But what's the relationship between QB and CG or VB, right? So it is charge equals to capacitance times the voltage, right? So then the rate of change of charge is the capacitance times the rate of change of voltage. But what is the rate of change of voltage? Is equal to the second derivative of the change of the flux because VB equal to d flux dt, right? Remember? We just say this here, right? Maybe here. V equal to d flux dt, right? So first derivative of VB is the second derivative of the flux. The whole goal, my whole goal is to represent IB in terms of this generalized coordinate. That's what I'm trying to do. Now then why I don't use QB? Because the next step I'm going to do is for Lagrangian. And you remember Lagrangian used two independent variables, the coordinate and the velocity. So it will be the flux and the rate of change of flux. Right? So I don't use QB now. Okay. Then how about IA? What is the current through A? Well, it equals to the current through the junction and also the current through the capacitor S, right? So this current equal to this plus this. IA equal to this plus this. Make sense? Now, but you need to be careful. The current through the junction, when I call it junction, right? It actually goes through the JJ and also the CJ, right? So let me be clear, right? What is the current through the junction? It is IC sine phi. I hope you remember this is the Josephson first Josephson equation, ICJ sine phi. How about the current through this CJ? Right? It is just like here that the current through a capacitor is just the capacitor times the second derivative of the flux, right? So it is also equal to Cj times the second derivative of the flux, but this flux is flux A, right? A, right? It's the flux across here. They all share the same flux. Am I clear? So similarly, I have the current through IC. So what is IC? IS, sorry, sorry, CS. I keep saying the wrong thing. This is CS phi A dot dot. Right? So the total current for A is IC psi phi, and then plus CS plus CJ phi A dot dot. Although it looks complicated, but what I have been doing is just a basic electrical circuit, Kirchhoff's current law. I plug in the current for the Josephson junction. I plug in the current through the capacitor. And another thing that is confusing is we used to use the voltage, but now we want to write it as the flux because of the reason I mentioned, right? Right? Then I now can equate them, right? IB is equal to CG plus B phi B dot dot equals to IC psi. Here I will jump a little bit and see if you can answer me why I can write this plus CS plus CJ plus A dot dot. On the left hand side, it is just IB. I write CG plus B dot dot plus phi B dot dot. On the right hand side is IA. I write IC psi phi plus CS plus CJ plus phi A dot dot. Why I make phi equal to phi A divided by this phi naught dash? First of all, what is phi naught dash? Do you remember? Huh? Reduce first quantum, yeah. Flux A is what? I mean phi A, sorry. It's just the same phi A. What is phi? This small letter phi. What is this? So how does the Josephson current depends on phi? What is phi? The phase, the Josephson phase, right? So we talk about the phase. I remind you again, you have two metals on either side, and they are macroscopic quantum objects because they are Cooper pairs, right? They share the same phase. I mean, each of them has the one phase, right? And this is the phase difference between these two metals. So this is the Josephson phase. And earlier in the last lecture, or maybe the one before, I already defined that if you want to have a flux associated with the Josephson junction, it's just equal to the phase times this reduced flux quantum. Right? And that's why I can do this. And the reason is also just because, I think I always make this like a review, right? The reason is also just because, you know, the base of the second Josephson law, we, right, JJ equals to this, the reduced flux quanta times d phi dt. And that's why we say, okay, this guy looks like the phi times the reduced flux quanta. So this one looks like d flux dt. And indeed, in classical or geometric inductor, this is exactly the equation, the relationship between the flux and the voltage, right? And it turned out that in Josephson junction, in the formalism, we can treat phase times reduced flux quantum as a flux. And this is the generalized coordinate for this Josephson junction. Okay? So based on this, then I would say I just rearrange the term. Let me see. Actually, I have everything already. Except that I'm going to write this as this guy equal to C summation. Okay? And that's it. And I call this equation 2. I think I have everything. So any question up to here? Right, so again, what we have done is just a simple circuit, just write down the simple circuit equation using KCL or KVL. You all can do that. The second thing we have done is we write voltage as a flux, the time derivative of flux. Right? And then the third thing is that we have this Josephson junction element, which has a special voltage current relationship. Instead of V over I or Cg dV dt, it is just given as this. You accept it. And we plug in. Then now we have two equations. Relate all the generalized coordinates together. Right? So how do we relate it? Then we say, right, combine equation 1 and 2 from, let's say, slides, should be 6 and 7, right? Then we get the equation of motion to be, let's look at this. I have flux speed dot dot here. This one also has flux speed dot dot here, right? Except that this is Cg on the left. So all I need to do is just multiply Cg to the left and right. Then I have Cg Vg dot minus flux A dot dot equals to. So why is that? Show you again. We had equation flux B dot dot equal to Vg dot dot minus flux A dot dot, right? So I multiply Cg to here, flux B dot dot, and this will be Cg times Vg dot dot minus flux A dot dot, right? Cg times, so here I miss a dot, should be Vg dot dot minus flux A dot dot. So sorry, did I make a mistake? Yeah, I have a mistake on my cheat sheet, but this one should be correct. Did I make any mistake here? I think I'm right. Yeah, should be second derivative for the voltage. Yeah. That's for what? CGIB dot dot equals to this whole thing, right? So I just need to copy this whole thing. IC sine phi A divided by the reducer flux quanta plus C summation phi A dot dot. So this is the classical, right? You can say this is classical equation of motion. So it basically tells us how the flux A will change as a function of time. All you need to is just to solve this equation. Okay, so nothing special, right? So far, it's just a mechanical operation. And again, to do this is not because we want to quantize the circuit, it's that we want to know what is the equation of motion, right? If we already knew that, we don't need to do that, right? But now we successfully represent this as a function of phi dot, and phi dot dot is here. So, then now we need to write the Lagrangian, but we don't know what it is. But we can guess, right? First of all, I recall what is Lagrangian. Lagrangian equals to the kinetic energy minus the potential energy, right? And we know that, we guess that, right? We can guess, it might not be correct because it depends on how complicated the circuit is. But we guess that this is just equal to the capacitive energy because we learned earlier the capacitive energy is associated with the kinetic energy, right? Minus the inductive energy. Okay? So this is, just recall what we learned earlier, right? So in other circuit. So we're going to guess. So if this is true, then I'm saying to guess the Lagrangian equals to capacitive energy. So among this whole circuit, I have this capacitive energy, right? 1 over 2 C summation VA squared. This is the capacitive energy associated with these two capacitors. So again, recall C summation equal to Cj plus Cs in this context. A little bit careful when we read different literature. Sometimes summation includes Cg, right? Just be careful. Here I only have Cj plus Cs. These two are the summation of the circuit. I mean, the sum of the capacitor. Is this okay? Are you okay that the capacitive energy across a capacitor is half CV squared? You should be able to prove it, right? But take it for granted again. Many of us learn in the elementary circuit already. If you don't know how to prove it, ask ChatGPT or talk to me. You really can prove to it, right? This simple one. Half CV squared. I have another capacitive energy in this circuit, right? Which is CGVB squared, because this is the voltage across CG. Okay. How about the inductive energy? The inductive energy will come as the Josephson energy. Okay. Again, I'm guessing. It's okay, it can be wrong, right? But I guess it is correct. So I'm guessing the Josephson energy is negative Ej cosine phi A divided by the reduced flux quantum. Make sense? Right? We know this already because in the last lecture we already showed that this is the Josephson junction, Josephson energy, right? I mean the energy stored in Josephson junction. Okay, so with that, then let's expand it. We definitely do not want VA, we want the coordinates. So this will be half C summation phi A dot square. And then this will be half CG. What is VB? VB, we don't want to introduce too many constants, right? But here I'm going to just use VG because VG is going to be given in a real problem because VG is the gate voltage we apply to this circuit. It's just equal to VG minus VA, and VA is just phi dot. Let me remind you, right? This is just VA. Right? So I need to be very careful about the sign, right? So this is plus minus, so it will be VG minus VA. And then the last term, just negative times negative equal to positive is EJ cosine phi A divided by phi naught dash. And I forgot the square here. So that is the Lagrangian, I guess. Okay? I need to check if it is correct. So now I need to check. How do I check? I'm going to plug this into the Lagrange equation. Right? Which means I'm going to apply, which means I require to prove that d dt, right, partial L partial Q I dot minus partial L partial Qi. I'm not proving, I mean I plug in to get the equation motion, right? To get the equation of motion. Right here it means equation of motion. Right. Now the point is, how many variables do I have in this system? As I said, we only have one, phi A, right? So, but here, Q0 equals to phi A, right? Only one variable in this circuit. Okay, let me see, do I still have space? Yes. Okay, so let me repeat one more time. What we are doing is just, we want to guess the Lagrangian. And the best way to guess this is based on our experience. We know Lagrangian is Ke minus Pe. And based on what we learned earlier, it's the capacitive energy minus the inductive energy. And then we write down the capacitive energy, subtract the inductive energy. We substitute all the voltage by the rates of change of flux, and do the necessary elimination of substitution of variable. Then we come up with the Lagrangian. And we want to check if this is correct. I will going to plug this into the Lagrange equation. And of course, I only have one variable, phi a. So I only have one Lagrange equation. And I need to check the equation derived by this Lagrange equation is going to be the same as the equation of motion we derived classically. Or it doesn't matter classically, or it is the same as the true equation of motion of this system. Okay? So let's check, right? It means check this equation. But now, of course, Qi equals to phi a, right? So to save time, I just copy it, but I will explain a little bit. What you want to do is just plug in the whole thing. Now, let's think about again. This is the Lagrangian. The first two depends on the velocity, the rates of change of flux A, right? The first two. The second two depends only on the coordinate, phi A, right? I keep saying coordinate and velocity. I hope it won't confuse you. So that's why for the first term is partial derivative with respect to Qi dot. So the last term has no effect because there's no Qi dot here. The second derivative is with respect to Qi, so that's the first two terms has no effect, right? And that's why when I plug in, I directly ignore those, so I only have partial, the first two terms, partial phi a. And then this one, the last term, which is the Josephson junction energy. Did I make a mistake here? So yeah, so this is another typo in my book then. This one should be, oh no, it is right, sorry. This is positive, yeah, so it was minus negative, yeah. So this is positive, right? Okay, so you do this derivative, it's easy, right? Just treat this as x, this is x squared, so this becomes half cx squared, so it becomes cx. With respect to this one, take out the 2, right? And then cg, and then you have this one. That is for the first term. Second term, with respect to phi a, cosine becomes sine, negative sine. And ej is there, but here this is, you scale by phi naught dash, so that's why I take out phi naught dash, right? Here you continue to have a second derivative, so you make this into second derivative. And then plus this guy. And then we further substitute phi c equal to, I did make a mistake here. That is V. So sorry, I did make a mistake here, right? This one should be only one dot for Vg. How do I come to here? So here should be only one dot. Now I cannot erase it. Right, so this mistake was from actually here. Can you tell me why I make this mistake? Why this is a mistake when I convert phi c to Vg?
Phi c should be the derivative of Vg.
Thank you. That's the mistake I make. It should be the derivative of Vg, right? But somehow I copied this dot to here. So my cheat sheet was correct. Yeah, okay. So I should not have a dot here, and I should not have a dot here. And then if we keep developing, doesn't matter. Yeah. So when you have Vg, you should have one less dot, right? Because the first derivative of flux equal to Vg, right? So here I just changed the variable. So from second derivative, go back to first derivative. Then you rearrange, you get this equation. And this equation is exactly the same as this one. Right? So then we say, yes, this is the correct Lagrangian. So this is, then I say, same as slide 8. And therefore, this is the correct equation motion, and therefore this is the correct Lagrangian. Any questions? Sorry for confusing you on the Ricci case. Yeah.
How come like the Lagrangian equations of the right of check has a negative sign, but then when you look at 3 in the yellow box, it's a plus.
There is another typo in the book. That should be negative. So many typos. Okay, this should be negative. Thank you. Good point, yeah. Yeah, but in principle, we studied this before, right? You should be able to correlate. Any other problem here? My God. Yeah, so it looks like we have not done anything. We only verified that we guessed the right Lagrangian. But that is easy for this simple circle. Maybe you are super confident, you don't have time, just guess it directly. Probably you are correct, right? But in a very complicated system, you need to be very careful. You need to know the equation of motion and then guess the Lagrangian and then get it. Because you might not know the equation of motion and you get it wrong because those capacitors are connecting in very sophisticated way. Okay. So you need to verify. Okay, so we have the Lagrangian. Then what does it mean? With Lagrangian, the next one we want to find is the momentum, right? Because you need to find the generalized momentum in order to get the Hamiltonian. Okay, so we follow the equation. So what is the momentum by definition? Q is the momentum here, equals to partial L, partial phi A dot, right? We use this definition, Q equal to partial L, partial V, right? V is the velocity, right? So by looking at this equation, of course, phi A dot is C sum phi A, the first term is C sum phi A dot. Second term is CG phi A dot plus phi C dot. And how about the last term? When you take the partial derivative with respect to phi A dot, what is the last term? Say again? 0, thank you. Because it's independent of phi A dot. Remember in Lagrangian, phi A and phi A dot are independent variable, right? The position and coordinates are independent variable. Good. So with this, I want to rewrite phi A dot equals to Q minus CG phi C dot divided by C summation plus CG. This is just a rearrange of variable. Should not be difficult, right? Just move CG phi C to the left, so minus CG phi C dot, and then you group the phi A dot divided by C sum plus CG. Anyone know why I need to find out phi A dot? Because our next step is to write the Hamiltonian. We do not want phi A dot to be there. So we're going to use this equation to replace phi A dot by Q. And you might worry, how about phi C dot? But phi C dot is just the VG, right? So it's not a variable we need to solve is a boundary condition. Okay. Okay, then we move forward. A lot of math. I've tried to save the time. The next step is now I have Lagrangian. I want to create a Hamiltonian. Hamiltonian by definition is sum over all the momentum times the velocity. But here we only have one variable, so only P0 and Q0 dot and minus the Lagrangian, right? So P0 is QA. Q0 is phi A dot, right? Because this is the coordinates derivative, which is velocity. This is the momentum. And then subtract the whole Lagrangian. And the rest are just math. But I want to tell you what happened in some places. For example, here first I'm going to replace phi A dot with the, am I right? I also got confused. Okay, so here I have not yet. I expand this to square, right? This is square, so I have half CG phi C square, but this is minus, right? So you get minus. I have phi A square, phi A dot square, so I combine with this phi A dot square times summation C summation CG divided by 2. I also have the cos term, negative 2 CG phi A dot phi C dot divided by 2, right? And then I try to group them. No, I actually, so what? Then I try to group them, group the phi A dot together, right? Maybe I can write it down so it's easier, or you can read the textbook, right? I try to group them, take out the phi A dot, then you have QA minus CG phi C dot, right? And finally, here I substitute the equation, right? Substitute slide 11. I substitute this equation, phi A dot equal to this big term. Just phi A dot, big term square. The rest I just copy phi A dot, big term, times this guy, and then subtract this. And you just go through them, you see that you can cancel some of the terms. But more importantly, right, at the end, from here to here, I ignore, not from here to here, sorry. Eventually, I get the bottom one, but from here to here, I ignore this term. Negative CG over 2 phi C dot square. Do you know why? That is because phi C dot is just equal to Vg. Negative Vg, right? And negative Vg is actually in an equation. It does not depend on the state. It is, if you write in the matrix form, it is just a diagonal matrix. So it only changed the global phase of the whole system when you exponentiate the Hamiltonian. And that's why we ignore this term. Okay? So eventually you will get these two terms, and that is the Hamiltonian of this whole circuit. I know this is very tedious, right? A lot of information. But it also shows that it's actually very beautiful. Although it looks like there are lots of math, but you actually can use mathematical to help you. The main point is that I hope you can appreciate we start with just a circuit and we carefully recognize which are the conjugate variable. And we just do the careful substitution, follow the procedure. Eventually come up with a Hamiltonian that depends on phi A and QA, which means depends on the coordinate and the momentum. And that is the total energy of this system. Okay, any question up to this step? Now, if no, Then let's rewrite this one. Then what is the next step? Easy, right? Can you now? Oh, actually, I already done already. Yeah, I done it already. I mean, already done. What is the next step? Promotes the conjugate variable. Right here is we promote the conjugate variables to operators. We've done that, right? Which is what? Q becomes Q hat. Phi A becomes phi A hat. And that's why we have this equation. Exactly the same as the last one. But we add the hat to it. That's the first thing. Now, second thing is that last time when we work with this Cooper-Bear box without external bias, we actually say that we prefer to work in the lumber operator and phase operator, right? So we're going to work in n hat and q and phi hat. Okay, so if this is the case, what is n hat again? We actually just repeating what we learned last time. It's just equal to negative qa hat divided by 2e, because we're talking about the number of Cooper pairs. So if you have a negative charge, you divide it by 2e, you will get the number of Cooper pairs. Is this okay? Right? Number of Cooper pairs has a 2e charge, right? But negative, right? So qa equal to negative 2en. Okay, that's the first thing, right? Now, then of course we also have this phi, the phase operator equal to the flux operator divided by the reduced flux quantum. So with this, I can rewrite the equations as this. Oh, okay, I also need to define one more thing, sorry. And also we want to define, this is just a definition, define Ng. This is the so-called offset charge equal to Cg times Vg divided by 2e. This is called offset charge. This basically represents, because of this capacitive coupling. For example, think about it, if I increase the voltage at this point, I will get more positive charge here. On the other side, here we'll get negative charge, right? Because it's a capacitor, plus Q minus Q. So basically, this is representing how much Cooper pair got induced by this external voltage. Remember this N, when we don't have this coupling, was about the number of excess Cooper pair in this Cooper pair box. But now you have this one, it will also help to induce some extra Cooper pairs. So Ng is related to that in that sense. Right? Let me see, I don't have enough space. So now with that, then I'm going to rewrite it H hat equals to Qa equals to negative 2En hat, right? And then Cg, Vg equal to 2ENG square divided by 2 summation C summation plus Cg minus Ej cosine. Instead of phi a divided by this, I just call it phi and hat, right? So now we go back to the phase and number operator instead of charge and flux operator. And they are just scaled by some numbers, right? So I continue to do this, I will get 4 EC times N hat minus NG square minus EJ cosine phi hat. Now, that was the one I confused you last time, right? The definition of EC, I keep changing, right? Do you remember what is EC? What is the meaning of EC? Charging energy. EC is the charging energy, but for what? Of one electron instead of one Cooper pair, right? In this case, its charging energy is half E squared divided by C summation plus CG. Okay, so if you plug in this guy, plug in this to here, right? You will see that this becomes 2E squared divided by summation of charge, right? And that is exactly what you have, because you have 2E squared. This is 2 become 4, but cancel by 2, so 2E squared. So basically, your total Hamiltonian is the charging energy minus the inductive energy. Now here, in the project, right, this is EC and EJ that you use to calculate the enharmonicity. You will see this in the printout when you do the pi EPR, right? So after all, this is the Hamiltonian. Is this okay? Any questions? No questions? Now, what's the difference? You should feel this is very similar to what we have learned earlier, isn't that? We have learned the Cooper pair box without external cap, right? But do you remember this equation? What is the difference between this one and that one? Basically, NG is 0. Right? In that equation, you don't have NG. And you have NG because of this coupling. Okay, so in the last case, we just hand-wavingly came up with this Hamiltonian. Here we rigorously gone through the Hamiltonian. And you see that it is what we did before was correct if we make NG equals 0, which makes sense if I don't have capacitor, or it means CG tends to 0, then of course NG is 0. Right? Then I will go back to the previous Hamiltonian. But the main point is that it is the same. So what we did earlier can be reused again. That's my message. Okay, so here we have the Hamiltonian of the Cooper pair box coupled to a voltage source.